Toss a ball straight up into the air, and it comes back down. It's an intuitive fact of life. But when it returns to your hand, is it traveling at the exact same speed it left with? Does it take the exact same amount of time to fall as it did to rise? To answer that, we first need to strip away the real world. Let's imagine a theoretical vacuum, a space completely devoid of air, wind, or any atmospheric interference. Here, only one force exists: gravity. In this pristine environment, gravity operates under a single absolute rule. It applies an eternal, constant downward acceleration to all objects of exactly 9.8 meters per second, every second. To solve physics problems in this space, we have to establish a strict mathematical sign convention. We define moving up as positive and moving down as negative. Because gravity is always pulling down, its acceleration is permanently locked at negative 9.8. There's a common trap here. Assuming when the ball reaches the peak of its flight and momentarily stops, gravity stops too. It doesn't. The object's velocity reaches absolute zero at the top, but gravity's downward acceleration remains exactly negative 9.8. The pole never pauses. Because that pole never changes, our vacuum environment acts as a perfect mathematical illusion. Every action going up has an exact mirrored reaction coming down. Look at the downward phase of that journey. On the way down, the ball's velocity and gravity's acceleration point in the same negative direction. Because they align, the ball's speed steadily increases as it falls. This is a velocity time graph tracking the flight. Because acceleration is a constant straight line, we find a strict law of time symmetry. The exact number of seconds the ball spends traveling upward is perfectly mirrored by the time it spends falling downward. The two halves are identical. The same rule applies to speed. If you measure the object's speed at any specific height during its ascent, it will be mathematically identical to its speed at that exact same height during the descent. This symmetry tells us that no kinetic energy is lost to the environment. The object returns to the launch point with the exact same energy it departed with. In a vacuum, nature plays a perfectly reversible tape. But the real world is messy, thick, and highly resistant to perfection. Flood that vacuum with atmosphere, and we introduce drag, or air resistance. Drag is a dissipative force that always opposes the direction of motion. Wherever the ball goes, the air pushes back. Let's analyze upward motion with this atmospheric rule. On a rising object, gravity pulls down. Because the object moves up, drag also pushes down. The drag vector stacks on gravity, creating a massive, combined net downward force. This double force causes a much sharper deceleration than gravity alone. Instead of the steady decline we saw in the vacuum, the velocity is forced to zero much faster. The object is rapidly robbed of its upward momentum. As a result, it reaches a lower maximum height in a shorter amount of time. Now, watch what happens on the downward motion. The object falls, so gravity pulls down as usual, but drag opposes motion, so it now pushes up. It fights directly against gravity. Our resulting net force vector is visibly shrunken. Because drag cancels part of gravity's pull, the object accelerates downward significantly slower than 9.8 meters per second squared. Look at the descent phase on our graph. The slope is shallow and lazy, completely destroying the symmetry we had in the vacuum. Air resistance acts as a constant thief of kinetic energy, forever breaking the mathematical mirror. The object decelerates aggressively on the way up, but accelerates lazily on the way down. This ensures that the time spent falling is strictly greater than the time spent rising. This raises an interesting hypothetical limit. What happens if the object is dropped from an extreme height and falls for a long time? As falling speed increases, upward drag gets stronger until it perfectly matches the downward weight. This is terminal velocity. When drag equals weight, net force drops to zero. Without net force, acceleration stops. The speed is locked. The ultimate fate of a falling object in an atmosphere is never infinite speed. It is a surrender to a constant, steady rate of descent. When solving kinematic problems, there is a golden rule to rely on. Whether air resistance is present or not, the velocity of the object at its very peak is always exactly zero. Avoid the two deadliest mistakes on an exam. First, forgetting the negative sign on downward gravity. Second, applying perfect vacuum symmetry to real-world atmospheric problems. This gives us the definitive answer to our opening question. Because of air resistance, the descent time is always longer than its ascent, and its return speed is always slower. When we watch a simple toss now, we can see the invisible battle of vectors dictating its path in real time. Gravity dictates the initial pull, but the atmosphere ensures no journey through the real world is ever truly free.